Hi, so today I will be presenting our latest work on understanding the potential of server-driven edge video analytics. I'm Qijun from the University of Chicago, and this is a joint work with my co-authors at U Chicago and at Princeton University. So in this talk, you will learn about one of the latest approach to design video analytics systems and the rationale behind the various design. So edge video analytics applications have been ubiquitous nowadays. For example, people deploy surveillance cameras in smart cities to collect videos in order to run analytics and monitor traffic conditions. They also use security cameras in smart homes and IoT devices to protect their properties from damage, and also in industrial settings to run analytics so that they could monitor the production space. Our goal here is to build high-performing and highly accurate video analytics systems with less network resource usage for these edge video analytics applications. So unlike streaming videos to human viewers to watch, when a video sensor sends live video feeds to a server-side deep neural network, abbreviated as DNN inference in real time, the major performance goal here is to maximize the inference accuracy under the presented camera to server bandwidth limit. This is pretty critical because most cameras are wirelessly connected with limited bandwidth or with pricey data plans. In this work, we're going to focus on object detection as an example usage case, and we're going to use the drop in bounding box confidence score as the inference accuracy metrics. So let's first take a look at two typical designs that have been recently adopted in designing video analytics systems. The first one features camera-side heuristics. In short, the system leverages local compute resources to decide how videos should be encoded by an encoder. Prior work features running a cheap model on the edge to determine which part of the video frame should be encoded in high quality, or simply deciding if the current video frame should be dropped in its entirety. Another design features a server-driven approach. In this design, there are two phases of video delivery. In the first phase, the camera or the video sensor is going to send a video frame with the regions that do not contain detected objects in low quality to the server for DNN inference. And the server is going to run inference on this first stream of video frames and return the results, which is in the form of a server-side feedback, indicating which regions might contain undetected objects. And this will be sent back to the camera. Upon receiving this feedback, the camera would know where it should encode the video in high quality. And it's going to encode this video and send it to the server again in the second phase. In short, server-driven design utilizes this server-side feedback to guide how videos should be encoded by a sender. So why are we not using camera-side heuristics in this work? And why are we instead focusing on the server-driven design? So the rationale here behind server-driven design is that edge cameras are incapable of running expensive DNN inference operations. In contrast, the server-driven design enables us to directly determine what to encode in high quality with the help of a compute-intensive server-side deep neural network. Due to the wide adoption of existing server-driven video analytics systems, we first do a comprehensive study on the performance of existing systems in this design space. And we find that these existing systems actually leave a lot of opportunities for further performance improvement on the table. So one particular problem we find with these systems is that they rely exclusively on region proposal results for generating the server-side feedback and for determining which part of the frame should be encoded in high quality in the second phase, as illustrated by the upper half of this slide. So we find that this approach is going to fail in two particular cases. In the first case, we can see in the lower left corner of this slide, we find that some pixels outside the region proposals could have very large influence to the final inference accuracy. And the second case, which can be seen on the lower right corner, we find that there are many pixels within these region proposals that are not influential as expected. because they might be associated with some smooth areas that are easy to detect. So we believe that these current systems, they are suboptimal in terms of their way of extracting the server-side feedback. So why is region proposal-based feedback suboptimal in its sense? And why would we need something new in this case? So the key insight here is that region proposals are derived from intermediate feature map results from the server-side deep neural networks. But in the ideal case, we would like to extract our feedback directly from the final inference result, because this is more aligned with our goal of improving the inference accuracy on the final server-side deep neural network inference accuracy. So next, we are going to introduce a new way of extracting server-side feedback in our work, which is our major contribution here. So our approach is called saliency-based feedback. So saliency on a higher level can be directly computed from the final inference result through backward propagation operations on the server-side deep neural network. So on a higher level, it's just like a derivative indicating the relative contribution of a pixel to the final inference accuracy. So in our case, we're computing this saliency in the way of computing the gradient of the confidence score sum with regard to the input pixel values. So it just gives us a better and more accurate model of the relative contribution of each pixel to the performance statistics we care about in the end. So as we can see in the workflow here, we're first going to extract the inference result from the server-side deep neural network. And then we run backward propagation operation on the result in order to obtain the saliency values. So these white little dots indicates the pixels with high saliency values. And after that, the server is going to run a very simple heuristics. So it's going to extract all the macro blocks with the highest sum of saliency values. And the server is going to mark these macro blocks as those that need to be encoded in high quality in future iterations. So this information will be sent back to the camera as a feedback. And in this case, the camera will know that which part of the frame should be encoded in high quality in future iterations. So the insight here is that saliency-based feedback can be extracted directly from the inference result through backward propagation operations. So it better fulfills our goal, and it's more aligned with our final goal of optimizing the final inference accuracy on the server-side deep neural network. So what's the advantage of using saliency, and what's the rationale of the intuition behind it? And why do we believe that it's going to work well in this case? So we believe that the key insight here is twofold. So first, saliency is able to better model and capture how much changing each pixel value would be able to influence the final inference accuracy. So as we can see in figure B here, for example, we have many pixels to the right side of the car bounding box or the car region proposal that are very influential to the inference accuracy, because not encoding these pixels in high quality would result in substantial accuracy drop as a form of performance penalty. This is something not captured in the existing region proposal-based feedback. If we take a look at figure A here in the slide. So yeah, it's able to better capture the pixels where we need to encode them with high quality. Otherwise, there would be heavy performance penalty here. So the second point here is saliency-based feedback enables us to better encode videos at a finer grain level. In other words, at a macro block level instead of at a region proposal level here. As we can see in figure C, this saliency-based feedback enables us to encode certain macro blocks within the region proposal with low quality, because based on our saliency computation, these pixels have very little influence on the final inference result if we change their values due to quality changes. So we also did some very empirical experiments to verify that saliency-based feedback could actually bring performance gain. So we first make the assumption that the client could have some, or the camera could have some saliency values computed from uncompressed video frames, so that it could have very accurate information about which pixels are very influential to the inference accuracy. So we find that the performance gain from this type of design is very large as compared to existing baselines. However, we noticed that although this is a pretty promising design, obtaining saliency values with uncompressed video frames is too expensive in terms of bandwidth usage, because we need to send the video frames in its uncompressed entirety to the server to extract the feedback. So as a next step, we explore practical system design through the choice of two key parameters that are related to the feedback extraction process. The first one is the video quality for feedback extraction. Like, what should be the quality of the video we send to the server in the first phase to extract this feedback information? The second is the frame rate of this feedback extraction. For example, we can extract it for every single frame, or we can do it on a much less frequent basis. So the intuition here is that we want to find some sweet spot in the design trade-offs, because clearly we could see some trade-offs behind these design choices. Let's start by considering one of the extreme case. So we could just extract saliency from uncompressed frames, and we can repeat this process for every single frame we have. In this case, we would have very accurate or very correct saliency values because the frames we use to extract the saliency are in high fidelity. But the problem here is that the bandwidth usage would be drastically large. On the other hand, we could also extract these saliency values from really compressed frames in low quality in the first phase. We could also drastically decrease the frequency at which we extract these feedback information. But the consequence is that we would have very inaccurate saliency values that are not very helpful to our goal, even though we have significantly cut down the bandwidth usage in this process. So the intuition here is that we believe there is a balance point in between the two extreme cases, which we would call a sweet spot. In this sweet spot, we are able to extract sufficiently accurate saliency values with relatively low bandwidth usage. And our goal is to find that sweet spot through a series of empirical experiments. So the details, such as the rationale behind the intuition of sweet spots and our exploration process of the sweet spot through empirical experiments. So these details can be found in our paper. So finally, we do some evaluation on our practical design through evaluating the accuracy degradation versus the network bandwidth trade-off in this plot. So the y-axis here is a drop in confidence score, and it reflects the degree of inference accuracy degradation of our results as compared to the result on the ground truth frames, which are the result on the uncompressed video frames. The x-axis here is a network bandwidth. So ideally, we would like the performance of our system to lie in the lower left corner of this plot. So next, we run the two baselines featuring two existing baselines in the server-driven design paradigm and see how they work out. We can see that the aforementioned design trade-offs can be clearly observed from the performance plots of these two baselines we choose. So when we see, for example, when we send high-quality frames in the first phase for feedback extraction, we would have accurate saliency values and thus less drop in confidence score on the y-axis. But the cost is that we have very large bandwidth usage. Then we evaluate our saliency-based approach on the same video data set. And here we show the sweet spot we have found through the empirical experiments. We can see that our saliency-based approach saves 43 to 57% of bandwidth usage without significantly compromising the inference accuracy. After that, we also evaluate our approach as well as the two baselines on another video data set featuring dramatically different contents. So there are a lot more different contents here. We also obtain about 15 to 20% of bandwidth saving and even achieves lower drop in confidence score. So we conclude that our saliency-based approach is able to show improvements on data sets with a wide variety of contents. So even though we have demonstrated exciting prospects and preliminary results for our saliency-based approach, this is an early stage work and has some limitations. So some people might ask, would our approach work on more vision tasks and vision DNNs? The answer here is yes, because when we're computing the saliency values with backpropagation, we're treating these vision DNNs as black boxes. So it would work on a much larger set of vision DNNs, but we do not guarantee more substantial performance gain in these occasions. Other people might ask, would our approach incur significant system usage? Our measurement shows that saliency computation incurs 82% more GPU memory usage than forward inference, which is a tricky question we want to resolve in the future. So also, we only focus on spatial video encoding, and in other words, the iframes in this work. Although we believe that temporal encoding could be incorporated rather straightforwardly, because to some extent, it's very similar to spatial encoding. So this is also part of our future work. So here's a brief summary of our conclusions and findings in this work. So current server-driven edge video analytics systems rely exclusively on region proposals for feedback extraction. And we believe that this is suboptimal because region proposals are extracted from intermediate feature map results instead of the final inference results. We also introduced saliency-based feedback to tackle this question, so we can directly model each pixel's contribution to the final inference accuracy through the final inference results. For practical system design, we explore what frame quality and frequency at which saliency and saliency-based feedback should be extracted. And our practical design shows some decent performance gain on a wide set of video featuring diverse contents. Thank you, and that's the end of our talk.